So concentration means you have read about the two terms, solute and solvent, right?
Yes, ma'am.
Okay, so the concentration refers to the amount of solute present in a given quantity of solvent. Given quantity of solvent or solution, you can say. So this is concentration. So there are different ways to express the concentration. These are very, very important for your exam and for your future aspects, right? So first, ways to define concentration terms can be molarity. Molarity. What is molarity? Anyone?
It is the amount of solute in 1 kg of solvent.
No, that's
1
molality.
liter.
No, that's molality.
Okay. Amount of substance
Yeah, go
of
ahead.
solute in 1 liter of
Yeah,
solvent.
yeah, in 1 liter. See the difference. You are talking about the molality, that is kg, right? In molality, we use the mass of solvent in kg, but in molarity, we use the volume of solution in liter. Got it? Just remember
Yes,
the
ma'am.
difference. It's very important. So, the molarity is it is most commonly used term, concentration unit, right? We use it in the lab for calculating molarity, for calculating concentration term, right? And the molarity is defined as the number of moles of solute dissolved in 1 liter of solution. Okay. So what could be the
Okay.
formula for molarity? It is denoted by capital M. Molarity can be calculated by the number of moles of solute. You have to divide it by volume of solution in liter. Got it?
Yes, ma'am.
Okay. We'll do the questions later in this class. Okay, but first we will see the basic concepts of this. After that, at last we will do the important questions of this chapter. Okay. So okay, the second one is your second concentration terms is your molality, and it is denoted by small m.
Ma'am.
Okay, there's a slight difference between molarity and molality. Molality says the number of moles of solute per kg, right? Present in per kg of solvent, right? And it is expressed as m, small m, just moles of take moles of solvent in numerator and just divide it by mass of solvent in kg, right? Next, we will talk about third one, which is your mass percent, which is W by W, right? So, what is mass percent?
Mass of the solute. divided by mass of the solution into 100.
Yeah, good. See, so for example, when I say 10 gram of C6H12O6, that is glucose, in water by mass. What does it mean? If I say 10 gram of glucose in water by mass. So by mass, I'm talking. So it means 10 gram of glucose is dissolved in how many grams? See, first, see, 10%, 10% of glucose in water. 10% of glucose in water, if I say. What does it mean? That 10 gram of glucose in how many grams of water? 90 grams of water, right? And if I say that the 10 grams of 10% of glucose means 10 gram of water in 100 gram of solution, right? And 10 gram of glucose in 90 gram of water, that is your solvent. Hope it is clear.
Yes, ma'am.
Okay, that's result in 100 gram of solution. When you add this 10 gram, that is your solute, 10 gram of solute, put it in 90 gram of water, then you will get 100 gram of solution, right? Sugar solution. So the percent, how can you calculate mass percent of any compound, any component?
The
Mass
formula?
of, the formula for this is mass of component in the solution, right? Just
Yes.
divide it by total mass of solution. Total mass of solution, that means total mass of solute plus mass of solvent. Total mass of solution into 100. Why? Because it is a percent. Got it? Got it? Any problem?
No, ma'am.
Okay. Can we move ahead?
Yes.
Yeah. Okay. So the fourth one is your, just like the previous one, volume percent. That is volume upon volume. Simply I'm writing the formula. Volume of component, volume percent of component can be calculated by volume of the component upon the total volume, upon the total volume of solution into 100. Multiply it by 100 and you will get the volume percent. Next one is your mass by volume percent. Mass by volume percent, that is M by V. Okay, so this unit is commonly used in medicine and pharmacy, right? Mass by volume percent. So it is defined as the name says, it is defined as the mass of solute which is dissolved in, because in the denominator section it is volume. So what you have to take is volume, right? Dissolved in 100 ml of the solution. Just in the numerator, put the mass of solute and divide it by volume of solution, right, into 100 because it is a percent again. Hope it is clear. If you have
Yes,
any
ma'am.
doubts, please ask in between. Okay, just to stop me and ask me to repeat. Next is your, again, it is very important, mole fraction. In these concentration terms, molarity, and this mole fraction is very, very important. Mole fraction, which is denoted by X. Okay. So if let's consider a binary mixture. Let's consider a binary mixture, and if the I'm talking about the binary mixture. Binary mixture. What is binary mixture?
It consists of two components.
Yeah, yeah, good. It consists of two components. That is your binary mixture. So if I say if it consists of two mixture, that is your A and B. Sorry, B. So the if the number of moles of A is Na and the number of moles of B is Nb, right? It is B, Nb. So what could be the mole fraction of A and mole fraction of B? So the mole fraction of A will be, the formula for this is the number of moles of component A, right? So the mole fraction of A will be the number of moles of component A upon total number of moles of all the components, right? So here are two components. So what will be the Na plus Nb? That's how you can calculate the mole fraction of component A. Got it? Similarly,
Yes, ma'am.
similarly, you can calculate the mole fraction of B also. What could be it? Number of moles of B. On numerator part, you will take B and B, right? And again, the total number of moles of all the component, that is Na plus Nb. Got it?
Yes, ma'am.
See here, uh, when I'm talking about binary mixture, so the mole fraction of Xa and Xb will be equals to 1. Okay,
Okay, ma'am.
equals to 1. So if you calculate one, if you know the one component mole fraction, then you can calculate the second by subtracting it by 1. For example, if Xa plus Xb equals to 1, so what could be Xb? Xb can be 1 minus Xa. Got it?
Yes, ma'am.
Okay, so understanding these concentration terms is very, very important for preparing solutions, right?
Yes,
Okay,
ma'am.
let's move to the next topic. Okay, one more concentration term is there, normality. Have you read about normality?
No, ma'am.
Okay, just a second. Okay, so let's start. So have you heard about the normality term?
No, ma'am.
No, seriously. Anyone?
No, ma'am.
Okay. So see, it is also a expressing the concentration term. It is also used for expressing the concentration. It's just like a normality, molality, etc. So in this, the definite write down the definition. Number of gram equivalent. I will show you. I will how to calculate the normality by giving examples. Number of gram equivalent of solute dissolved in per liter, dissolved per liter. Of the solution at a certain temperature. Okay, so write on the formula for normality is denoted by capital M, and we use the weight of solute on equivalent weight into volume in milliliter. Okay,
Okay, ma'am.
as you are taking the volume in milliliter, so just multiply it by 100. Okay, so this is the formula. But what about the, if I ask you, tell me what is the difference between molecular weight and equivalent weight? What is the difference between molecular weight and equivalent weight? Anyone? No one? Okay. So see, the molecular weight, basically, you all are aware of molecular weight. So molecular weight, we use the sum of atomic masses, all the atoms in the molecule, right?
Yes.
Molecular weight of a molecule is the sum of all the atomic masses, all the atoms in the molecule. But when I say equivalent weight is the mass of equivalent weight is the mass of substance that can combine with or displace that can combine or displace 1 mole of hydrogen atoms. Or you can say 1 mole of electrons in a chemical reaction. Right. So simply, you can find equivalent weight by dividing it by n factor, right? Molecular weight divided by n factor. So where n factor is what? N is the number of moles of reactive species, like example protons or electrons, right? That 1 mole of the substance can provide or react with. Let's take one example so that it can be clarified to you. For example, uh, if I ask you to find the equivalent weight of, what will be the equivalent weight of H2SO4, sulfuric acid, right? So first calculate the what is the molecular weight of H2SO4? Tell me. Find the molecular weight of H2SO4 and tell me. Anyone? If you don't know, please say no. So just I can proceed.
Um, 90,
Yeah, 90.
98.
Yeah, good, good. The molecular weight of H2SO4 will be 98. How? See, uh,
With the two into
H2SO4.
atomic mass.
Yeah. So the hydrogen atomic mass is 1 and the number of hydrogen here is 2. The sulfur atomic mass is 32 and here sulfur is 1 plus oxygen atomic mass is 16 into 4. What will you get? You will get 2
98.
plus 32 plus 64. That is your 98 gram per mole. Always say the unit also. So this is the
Okay.
molecular weight. Okay. So see, uh, equivalent weight. Equivalent weight, how, what is the formula for equivalent weight? Equivalent weight equals to molecular weight upon n factor. Now, how can you calculate the n factor of this? So, see here, H2SO4. Now, here, you just have to see how many protons this H2SO4 can give, right? How many? So, you can say that there are 2 hydrogen, right? So,
Yes, ma'am.
it can donate 2 protons, 2 protons, that is 2H plus ion, right, in reaction. So what will be the n factor of this? This is your 2. Got it?
Okay, ma'am.
Another example, let's take for HCl. What will be the n factor of HCl? Just you have to see how many protons it can give. You just have to see the H plus ion. So HCl will
Mm,
break down into H plus and Cl minus. So there are only 1 protons, right? So what will be the
yes,
n
ma'am.
factor of HCl? 1. Got
One.
it?
Yes, ma'am.
Clear?
Yes, ma'am.
Okay. So what will be the equivalent weight? Equivalent weight of H2SO4 will be, molecular weight will be 98 divided by 2, right?
Yes, ma'am.
H2SO4 n factor is 2. So so from here it will be 49.
49.
49 gram equivalent, gram per
Um,
equivalent, you will say. Got it? I hope
Yes,
it's
ma'am.
clear.
Yes, ma'am.
Don't forget it. It's very basic. Okay. So now I hope it's all clear. Now let's move
Yes,
to the
ma'am.
next topic. It's a huge chapter, right? And there are many important topics also that we have to cover or revise. Okay, so the next one is your solubility of gas in liquid. So here, when we talk about the solubility of gas in liquid, uh, we just thought about Henry's law, right? Henry's law. What is
Yes.
Henry's law?
It states that the partial pressure of a gas in vapor phase is directly proportional to the mole fraction of the gas.
Very good, very good. It's Mariam. Mariam, is that
Yes,
you?
ma'am.
Yeah,
Yes, ma'am.
very good, Mariam. Henry's law. Okay, I will not go in details, right?
Okay.
Just we are doing revision here. So, what is Henry's law? As Mariam said, the statement could be the partial pressure, that is P, of the gas in vapor pressure. It is proportional to the, here P is proportional to the mole fraction, right? Mole fraction, that is X of the gas in the solution. This is known as Henry's law. If this proportionality sign will be removed, what you will get? KH into X.
Correct.
And what is KH here? So KH
It
here
is the
is,
Henry's constant.
yeah, it is a Henry's constant. Constant, okay? And
Yes.
this KH, sorry, KH is inversely proportional to solubility. Just remember it. KH is inversely proportional to solubility. So what does it mean? Higher the value of KH at a particular temperature, lower is the solubility. Okay? And vice versa. Okay, and KH is directly proportional to temperature. The more the temperature it is, the more the KH value. Okay,
Okay.
temperature. Okay, next we will talk about the vapor pressure of solution. Okay, so vapor pressure, the pressure exerted by the vapor above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure. What is vapor pressure? The pressure which are exerted by the vapors, right, above the liquid
Yes,
surface
ma'am.
in equilibrium with the liquid at a given temperature is known as vapor pressure. In vapor pressure, we will talk about Raoult's law, which is again a very, very important topic here. So let's see the Raoult's law. What does Raoult's law says? Anyone? Tell me some equation. Tell me anything about
The
Raoult's law.
Raoult's law for volatile
Yeah, these are
things
for
is
volatile solutes. Good.
the pressure of a gas is directly proportional to its mole fraction.
Yeah, okay, good. Okay, see. So Raoult's law is basically for solutions containing volatile subsolutes. Okay. Now this law states that, okay, this law states that for a solution of volatile solutes, the partial vapor pressure, let's suppose we are talking about component 1 and component 2. So the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. So for component A, or 1, you can say, what will be the partial pressure? That is P1 is directly proportional to X1. Okay.
Yes, ma'am.
And when you remove this proportionality sign, what will you get? P P naught 1 into X1. Are you writing?
Yes, ma'am.
Okay, write along with me. It's not a theoretical one. It's just like maths. Chemistry is just like maths. You just have to practice a lot. So where P1 is your partial vapor pressure, partial, I'm writing vapor pressure as a VP, okay? Pressure of
Okay.
component 1. And what is P1 not here? Hmm?
Pressure, partial pressure.
Pure or pure component.
Okay.
Vapor pressure. When I'm using not here, so just remember it is for pure. Vapor pressure of pure component 1. And x1 here is the mole fraction of pure component 1, not pure 1, mole fraction of component 1. Okay,
Okay.
similar to that, just let's write for component 2 also. For component 2, what it could be? P2 is directly proportional to x2, right? And when you remove the proportionality sign, what it could be? P2 not into x2. Again, same thing. P2 here is your partial vapor pressure of component 2. P2 naught here is your partial vapor pressure of pure component, right? And X2 here is your mole fraction of component 2. Now, according to Dalton's law of partial pressure, the total pressure over the solution phase over the solution and the container will be the sum of P1 and P2. Sum of the partial. Sometimes they ask the derivation also,
Okay.
which is given by what it could be. P total partial pressure will be equals to P1 plus P2. Now substitute the value of P1 and P2 here. Just substitute the value, that is P total equals to P1 will be x1 P1 not P1 not plus x2 P2 not. Got it? As I told you that the mole fraction of x2 components like binary in a binary mixture, that x1 plus x2 is equals to 1, right? So
Mhm.
can you substitute this by x2 equals to, can you write this x2 equals to
Okay.
1 minus x2, right? So substitute this in equation 1, or you can write it also like x2 x1 equals to 1 minus x2. Okay, so put it in this equation. 1 x1 could be 1 minus x2 into p1 naught plus x2 plus p2 naught. Got it? Clear till here?
Yes, ma'am.
Okay. Now just multiply, just
Yes, ma'am.
open the bracket and P1 naught minus here x2 P1 naught plus x2 P2 naught. Okay, just P1 naught, just take common x2 plus P2 naught I'm writing this first, then I'm writing this one. Because I have written a positive charge here, so I'm writing this x2 p2 not first, right? So here p2
Okay.
p2 not minus p1 not into x2. So this will be your p total, right? This equation is very, very important. Why? Because from this equation, there are some conclusions. Like first, from the above equation, following conclusions can be drawn like first, total vapor pressure, total vapor pressure over the solution can be related to the mole fraction of any one component, of any one component. Got it? Now see here, uh, I just substitute this x1 equals to 1 minus x2. You can also substitute it like x2 equals to 1 minus x1, right? So you will get the
Yes,
different
ma'am.
equation. That's why I'm writing this steps, right? Writing this point that total vapor pressure over the solution can be related to the mole fraction of any one component, right? Second one is your total
Yes,
vapor
ma'am.
pressure, total vapor pressure over the solution varies linearly. It varies linearly with the mole fraction of component 2. It will be more clear with the graph. Third one is by this equation, third point could be depending on the vapor pressures of the pure components 1 and 2, the total vapor pressure over the solution decreases. This is the decreasing sign. Okay, decreases or increases with the increase of the mole fraction. Increase of the mole fraction of component A.
Okay.
Right. So the total vapor
Yes, ma'am.
pressure increases either or decreases with the increase in the mole fraction of component 1. Got it? Point clear?
Yes, ma'am. Yes, ma'am.
Okay. Okay. Let's move ahead. Yeah. So, see the graph here. I'm drawing a graph here. So this is basically a mole fraction versus on the x-axis we are taking mole fraction. On the y-axis we are taking vapor pressure. Okay, and here at this point
Okay.
x1 equals to 1 and x2 equals to 0. x1 is your mole fraction of first component and x2 is your mole fraction of second component. But at this point, x1 becomes 1, sorry, 0, just opposite of that. Yeah, x1 becomes 0, and here x2, that is mole fraction of component 2, becomes 1. Clear? Now see, this is basically a graph of Rolle's law.
Okay.
Here's a P1 naught, that's a partial vapor pressure of pure component 1 and the partial pressure of pure component 2. Okay, this is the dash line which shows the partial pressure of first component, right? And this dotted line shows the partial pressure of P2. So this is your first line, and this is your second line, and this is your third one. And this third line, it shows this equation. This is a linear line which shows P total P1 plus P2. Got it? Till here, any confusion? So the plot of P1 or P2 versus the mole fraction of x1, x2 for a solution gives a linear plot. This is basically a linear plot, right? So here these two dashed lines, like this one first line and the second line, represent the partial pressure of the component 1 and component 2. Right? This is partial pressure of component 2, and this line shows the partial pressure of component 1. Okay,
Right.
and yeah,
Uh,
any doubt?
No, ma'am.
Okay, so it can be seen from the plot that P1 and P2 are directly proportional to x1 and x2 respectively, right? This x1, this first line and the second line, that is P1 and P2. These are basically directly proportional to each other, and this total pressure, this P total, that is your third line. It is given by the solid mark 3 in the graph. Are you seeing this line? This line shows the P total, that is P1 plus P2. Okay, this is basically a Rolle's law
Okay.
graph. This is a Rolle's law graph. Clear? And it comes from that
Okay.
equation.
Yes, ma'am. Yes.
Yeah, that equation. Next is your, okay. See, here the composition of vapor pressure in equilibrium with the solution is is determined by the partial pressure of the components. Okay, so if I say y1 and y2 are the mole fraction of the component 1 and 2 respectively, then using Dalton's law, what will be the vapor pressure of those two components? P1 will be y1 into P total. Got it? And what will be the P2?
Okay.
Y2 into P total.
Okay.
Now here comes a special case of Rawls law. Uh, write down Rawls law as a special case of Henry's law. So what it says that in the solution of a gas, if a gas solution in a solution of gas in a liquid, we are talking about gas in a liquid type of solution. So Rawls law becomes a special case of Henry's law, in which Ah, that is a Henry's constant, becomes equal to pure component, partial pressure of pure component, that is your P naught. Got it? So it's a special case of Henry's law, which specifies that uh, uh, in a solution of a gas or liquid, Rawls law becomes a special case of Henry's law, in which KH becomes equals to pure component, that is your P naught. Right? KH becomes equals to P naught. Clear? Clear till here? Any doubt? Any doubt? If there's any
No,
doubt, you
ma'am,
can
no
ask.
doubt.
Okay. So now we will talk about the ideal and non-ideal solution. So what are ideal and non-ideal solutions, anyone?
Ideal solutions are the solutions which obey the Raoult law over the entire range of concentration.
Yeah, good. And the non-ideal solutions are those that do not obey
And
this
the
law.
non-ideal solution,
Yeah.
yes, ma'am.
So hope it is clear to all. So, let's see the ideal solution the non-ideal one. Basically, in this, the graph is very important. The deviation is very important. That is a positive and negative deviation in case of non-ideal one. Mm. Okay, so what are the ideal solution? Which obey Rolle's law over the entire range of concentration, but that do not obey. Okay, in this case, in ideal solution, the enthalpy change of mixture is zero. That equals to zero. But in that case, it is not equals to zero. The enthalpy change of mixture is not equals to zero. In ideal one, the volume change of mixture is equals to zero. But in non-ideal one, the volume change of mixture is not equals to zero. Got it?
Yes, ma'am.
Next is your in ideal solution, the force of attraction. Okay, see. So AA bond and AA and BB interactions are equal to that of AB, equal to AB interactions. Okay, so the force of attraction of AA and BB interaction are just similar to that of AB interactions. But in this case, non-ideal one, it is different. Okay, and we will talk about the non-ideal solution in details. But before that, first let me clear the ideal one solution. For example, can you please give me some examples of ideal solutions? It can be asked in 1 mark question in your board. What are ideal solutions and give 1 or 2 examples of this. So the examples include the solution of N-hexane,
And
hence,
benzene.
yeah, and N-heptane, you can say, N-heptane, and the solution of bromoethane and chloroethane, bromoethane
Yes, ma'am.
plus chloroethane. This can be asked in 1 mark question. Another example could be benzene plus toluene, etc. Right? These are nearly ideal in behavior. Now let's talk about the non-ideal solution. So non-ideal solutions are those that do not obey the Raoult's law, right? And there are they show
Yes.
deviations. Like the first one is negative deviation, and the second one is your positive deviation. See, the vapor pressure of these solutions could show first one is your, let's talk about the negative deviation, right? And could be positive deviation. Okay. They sometimes ask differentiate between ideal and non-ideal
Yes.
solution, right? So it's again important topic.
Okay.
Concentrate here. So the negative deviation shows in which the delta H mix enthalpy mixture of is less than zero. right? Less than 0 means it will be negative. Delta H equals to, this will be negative, right? But in this, delta H, enthalpy change will be greater than 0, which is positive. Positive. Second point would be the volume change of mixture. Again, it is negative, and in this case, positive deviation, it shows positive, right? The volume will be positive. That is your greater than 0. Got it? There, see the graph of this. In the negative one, okay, here the mole fraction was on the y-axis, vapor pressure was there. Okay. Hmm. So just remember the graph of Rolle's law. Remember the graph of Rolle's law? See, that was for ideal one, right? In the Rolle's law, this graph, yeah, this graph was for ideal one, the one that obeys Rolle's law, right? So this is for ideal one, but in the non-ideal solution, they don't obey the Rolle's law and they show certain deviation from this graph, right? So let's see the graph one by one for positive and one for negative. Next for negative one. Okay, see, it was the this was the graph here. P1 naught was there. P1 naught here. P2 naught. Here x1 was 0 and x2 was 1. But here x1 was 1 and x2 was 0. First, make the graph that was for ideal one. Okay. In this case also, this was for P1 equals P total. This line was for P total, that is for P1 plus P2. Clear? Now see, in positive deviation, no,
Yes,
so
ma'am.
this is for negative deviation. So in the case of negative deviation, the graph goes like this, just beyond this line. This, right? Again, just beyond this line. Just don't mind my drawing. Just understand the concept here. So for the ideal one, it was like, yeah. So this is the uh, graph which shows a negative deviation from the Rolle's law. That is for non-ideal solution. And this line, see this line, this red line, it shows the vapor pressure of solution. This shows the vapor pressure of solution, right? That is your P total, P1 plus P naught. And this shows your P2 naught, and this shows your P1 naught, right? In case of non-ideal solution in negative deviation. right? In negative deviation, the
Yes.
graph, this line will be beyond this ideal one, right? Now let's see the graph for
Yes.
positive one. Here we will mole fraction. Just go through it. X1 equals to 0. You can follow the NCRT for this graph. That's very important for your exam, right? Just first make the graph for ideal. That was for Rolle's law. This was the ideal line, right? This was for P1. Sorry, P total equals to P1 plus P naught. P1 plus P2. Okay. What happens in this?
Okay.
The positive deviation. This line just goes like this, above this line, right? And this goes above this line. And this P2 naught line goes above this line, right? So it becomes P total. This line, this red color line, dotted line shows the vapor pressure of solution, which is your P total, right? And this line shows P2 naught, and this line shows P1 naught. Clear? I hope
Yes,
it
ma'am.
is clear. My drawing is not
Yes, ma'am.
not good, but please try to understand the concept. Okay, you can just go through your NCRT book for this graph. It is very important for your exam. Okay, and in this negative deviation, the bond. Let's talk about the bond. In the negative deviation, AB bond, AB interactions are stronger, are much stronger than those between AA or BB. Got it? But in this case, in positive deviation, the AB interactions are weaker. AB interactions are weaker than those between AA and AB and AA and BB. Sorry. Write down the examples also because sometimes they also ask the example. Okay, so for the negative one, a mixture of HCl and water, HCl and water, or the mixture of acetone, acetone and chloroform, that is CaCl3. And when I talk about the positive deviation of non-ideal solution, what could be the example? Mixture of, it could be mixture of ethanol,
Acetone and ethanol.
ethanol plus water, or acetone or ethanol, acetone plus ethanol. Okay, got it?
Yes. Yes, ma'am.
Can I go ahead?
Yes, ma'am.
Okay, next, write down the azeotropic mixtures. What are azeotropic mixtures?
They are binary mixture. They cannot be separated by fractional distillation. and they have the same composition in liquid and vapor phase.
Okay. Basically, a
And
miscible
there was one
liquids.
more point.
Completely. These are basically a completely miscible liquids, which boils at constant temperature
Okay.
and can distill over without any change in temperature or any change in composition also. Azeotropic mixtures. Again, they can ask in a definition, explain the azeotropic mixtures with examples, right? In a one mark question, they can ask. So write down the azeotropic mixtures, solutions of completely immiscible liquids, which boils at constant temperature and can distilled over without any change in composition. Right? So these are called the azeotropes or azeotropic mixtures. Now there are two types of azeotropic mixtures. What are they? First one is your maximum boiling,
Maximum, minimum.
maximum boiling azeotropes. And the second one is your minimum boiling azeotropes. Minimum boiling, minimum boiling azeotropes. Okay. So what are maximum boiling azeotropes and what are minimum boiling azeotropes?
Maximum boiling isotope, they have negative deviation, and
Yeah,
minimum boiling isotope, high positive deviation.
yeah, very good. So, maximum boiling azeotropes are those azeotropes which shows large deviation, negative deviation from Rod's law. And minimum are those that shows large deviation, positive deviation. Okay. Okay, now let's move to the
Yes.
next topic that is your colligative properties. So, in colligative properties, we will study the four properties like first, relative lowering of vapor pressure, depression in freezing point, elevation in boiling point, and the last one is the osmosis and osmotic pressure. Okay, so let's see one by one. First one, relative lowering of vapor pressure. So I will not go in details. As you all are aware of this relative lowering of vapor pressure, that it is for an ideal solution which contains non-volatile solute, right? When the non-volatile solute is equal to the mole fraction of the solute at a given temperature. So here, Rod's law for non-volatile solute is given by P naught minus P upon T. Most of the question in your board exams comes from this only, colligative properties, right? Colligative properties and your ideal and non-ideal solution, right? And your Rod's law. So these are basically very important from this chapter. Just go through it, and if you have any problem, just contact me, right? And at last, we will do some important questions also, so that it can be more clarified. P naught minus P upon P naught equals to, you can calculate the X of solute, right? That is a mole fraction of solute. And can also be calculated by N upon N plus 1. Okay. So P naught here is your
Okay.
vapor pressure. P naught here is your vapor pressure of pure solvent. P here is your vapor pressure of solution, right? And X of solute, as you all know that that is mole fraction of solute. And N here is the number of moles of solute. And capital N here is the number of moles of solvent. Number of moles of solvent. Now, the one more relation is there, that is M dash is equals to W M upon, this is a capital W, right? Into P naught minus P upon P naught. So here M dash is your molecular mass of solute. You can calculate the molecular mass of solute by this formula. And small w here is your given mass of solute. Capital W is your given mass of solvent. And capital M will be your molecular mass of solvent. Okay, right. Just remember this formula. Next is your depression in freezing point. Okay, so depression in freezing point. So so these colligative properties are just for a non-volatile one, right? So when a non-volatile
Yeah.
solution is added, right? When a non-volatile solution, solute is added to a solvent, what happens? Anyone? What happens? See, so when you add a non-volatile solute in a solvent, the freezing point of a solution is always lower than that of the pure solvent, right? As the vapor pressure of the solvent decreases in the presence of non-volatile solute. The vapor pressure of the solvent decreases in the presence of a non-volatile solution. And this difference is, in freezing point is known as the depression in freezing point, which is denoted by delta TF. Okay, again I'm repeating, when you add non-volatile solute to a solvent, what happens? The vapor pressure of the solvent decreases, right, in the presence of a non-volatile solute, and is always lower than that of the pure solvent. Clear? And
Yes, ma'am.
delta TF can be calculated using this formula, that is delta TF equals to KF into M. Now, what is delta TF here? So you all know that delta TF is the depression in freezing point.
Yes, ma'am.
Okay. And Kf here is your molar. This is your molar depression constant. This is your molar depression constant. Or you can say that cryoscopic constant also. And M here is your molality. Molality. Here, another formula here is you can calculate the molecular mass of solute using this formula, that is your Kf, multiply it by W upon 1000 into delta Tf to W. W here is capital W, here is in gram. So M dash here is your molecular mass of solute, and Kf is your molar depression constant. Small w is your mass of given mass of your solute, and capital is your given mass of solvent, right? So you can calculate uh, when these four things are given in your question, then you can solve it for molecular mass of solute, right? All the notations have their own
Yes,
meaning.
ma'am.
Yeah. So it will be more clear when we do some numerical questions, right? Elevation in boiling
Yes,
point. Elevation in boiling point. What is elevation in boiling point? Basically, it is denoted by delta TB, okay? And delta
okay, ma'am.
TB is equals to KB into M. Remember the relation. Delta TB equals to KB into M. So here, delta TB is your elevation in boiling point. KB is your molar. This is your molar elevation constant, or you can say that ebullioscopic, right? Ebullioscopic constant. And M is your molality. Molality. Again, one another formula for calculating the molar molecule of solute will be M dash equals to KB into W 1000 upon here you can see delta TB into, right. Yeah. So these are very important formula. Next is your osmosis and osmotic pressure. So what is osmosis? Anyone? Osmosis?
When the solute particles they move from higher, higher
Huh?
when the solute particles move from higher concentrations to lower concentrations.
Okay. Using do just don't forget to add this word semi-permeable membrane. Through a semi-permeable membrane, right? So what does osmosis means? The process of flow of solvent molecules through the semi-permeable membrane from the solution of higher concentration to lower concentration. Now tell me, what is a reverse osmosis? What is reverse osmosis?
Reverse osmosis is when the solute particles they move from lower concentration to higher concentration in a semi-permeable membrane.
Okay. And when the pressure applied on the solution is greater than that of the osmotic pressure, right? So,
Yes.
yeah. So see here, mm, osmotic pressure, which is given by pi, right? It is denoted by pi equals to CRT. Remember this. Yeah, this is very important. Remember this relation, that is osmotic pressure is equals to the product of concentration, gas constant, and the temperature. Okay, here pi is your osmotic pressure. This is your osmotic pressure. The C is your concentration. Concentration of what? Concentration of solution. R is your gas constant, and T is your temperature. Okay, this relation can also be given by pi equals to, what's the concentration here? Concentration is the N by V, right? N upon V, that is that is your number of moles of solute divided by volume into RT. Okay. Again, this relation is also very important. Here, N is your number of moles of solute. V is your volume, and RT, as you all know, that gas constant temperature. Next is your M dash. Again, this relation is also important. It's a relation with molecular mass of solute and W RT upon pi V. Right. Again, this is important. Hope you get my point.